In section 7.4, we'll be discussing average value. So if you think about how to find the average of a set of numbers, just like from a previous math class, you add up all the numbers and divide by the number of numbers that you have. It's the same idea here, but a little bit more complex. If we are looking for the average of a function, f of x, we would think about taking the average of its y values, but there's a bunch of different y values between 2 points. I can't just have a distinct set of numbers to add up. And so if we're adding up all the y values together, that's really giving us the area under the curve, which is the integral from a to b of our function. And then instead of dividing by the number of numbers that I have, I'm going to divide by the width. So I'm on the interval from a to b, so my formula is 1 over b minus a times the integral from a to b f of x dx. Let's take a look at example number 1. Notice this calculator symbol here. It means we are going to use a calculator on this problem. We have f of x equals 2x e to the negative x squared. We want to find the average value of f on the interval 2 to 5. So we're going to use this same formula, 1 over 5 minus 2. I'm using these as my a and my b, times the integral from 2 to 5 of f of x, which is 2x e to the negative x squared. You could also just write f of x. And then I'm going to calculate that. Since this is a calculator problem, I can go ahead and put the function in my y equals. I've done that already. And then back on my home screen, I'm going to do 1 divided by 3. And then the integral, remember integral is math 9, from 2 to 5 of y1 and then don't forget your dx. You can also just type that function in instead of saving it as y1, but since I already put it in y1 because I will use this in a and b, I can just use the y1 that's there. And so I get an answer of 0.006. Make sure you're going to 3 decimal places. Now in part B, it asks us to find the average value of f prime of x. I'll still set it up the same way, but now my integrand is f prime of x instead of f. Now one way to do this would be to actually take the derivative of 2x e to the negative x squared and then integrate that on my calculator. Taking that derivative though would mean I would have to use product rule and chain rule, and it would get a little messy. So maybe we can think about it a different way. If I integrate f prime, that would give me f. And then I evaluate it from 2 to 5. That's f of 5 minus f of 2 over 5 minus 2. So the top part comes from taking the antiderivative of f prime from 2 to 5, and then I still divide by 5 minus 2. Notice this is the average rate of change of f. If you remember that formula, f of b minus f of a over b minus a. And that's because f prime is the rate of change of f. And so we're doing the average of that. In a, this was the average of f. Here, this is the average of f prime, or the average rate of change of f. Now to calculate that, I'm going to go back to my calculator on my home screen. I want to use a fraction here. Now I can use the division symbol like I did with the 1/3. I'll have to be careful with parentheses. But there is a shortcut if you have the updated version of the calculator. If you hit alpha y equals, number 1, n over d is numerator over denominator. This is going to give me a fraction here. It helps me keep track of what's in the numerator versus denominator. A little easier to look at than using all the parentheses. So we're going to do alpha trace to get my y1. And I'm going to do y1 of 5 minus alpha trace y1 of 2 all over 5 minus 2. So in the same way that we wrote f of 5 minus f of 2, we can do that this way so that we don't have to hand type in the 5 and the 2 into my f of x function. It will just calculate it for me. And I get negative 0.024. So let's try a problem without a calculator now. In number 2, we're finding the average value of f of x, which is 3x squared minus 2x, on the interval from 1 to 4. So again, we'll start out with that formula, 1 over 4 minus 1, times the integral from 1 to 4 of 3x squared minus 2x. Now in this case, we're not using our calculator, so we will go ahead and find this integral, which means we need to take the antiderivative. So I'm going to do 1/3. The antiderivative of 3x squared minus 2x is x cubed minus x squared. I'm evaluating it from 1 to 4. Then I'll plug in, keep the 1/3 out in front. I have 4 cubed minus 4 squared minus 1 cubed minus 1 squared. Now this is an okay place to leave my answer on the AP test. As long as I've actually plugged in those numbers, then I can leave it there. But on this problem, and probably in your Delta Math, it will say simplify your answer. So we're going to go ahead and simplify it. We've got 1/3 of 64 minus 16, that's 48. Minus 1 minus 1 is 0. So we've got 1/3 of 48, and our answer is 16. Okay, now let's try a piecewise function. So it does ask us to determine the average value of f and on the interval from -2 to 2. So when I start this out, I'm going to start it the same as I've done before. So I'll write 1/2 minus -2 times the integral from -2 to 2 of f of x. That is average value of f. What's different is that I have two different definitions for f. The first one is 3x squared plus 6 when my x is less than 1, and then -3x squared for x greater than 1. And this graph does not have to be continuous in order for me to integrate it. Let's simplify a little bit. I've got 1/4 there. That 1/4 is going to stay out in front. Notice I'm taking the average value of the whole function, so I'm going to divide by this whole width. It's not the width of the separate intervals. In order to integrate this piecewise function, I will just integrate it over their specific domains. So for the first function, 3x squared plus 6, I need to pay attention to where it starts and where it stops. So it's going to start at -2, and it will end at x equals 1. And then I'm going to add on the integral for the other piece of f of x. That starts at 1. It will end at my right endpoint 2. And I'm integrating -3x squared dx. Make sure you write this step out. If this is a free response problem, you're going to get most of your points for writing your setup. Now we can integrate each of these individually. The 1/4 stays in front. Taking your antiderivative, this would be x cubed plus 6x, evaluated from -2 to 1, plus -x cubed, evaluated from 1 to 2. I can't stop yet. I still need to plug in those numbers. 1/4 times 1 cubed plus 6 times 1 minus -2 cubed. I need another parenthesis there, plus 6 times -2. And then plus -2 cubed minus -1 cubed. You can change that to a plus if you want. And my bracket there. Now this would be an okay way to leave it on the AP test. However, we are going to simplify this. You can go ahead and simplify it on your own. You should get 5 for your answer. So remember back from first semester, we talked about that the derivative of an amount would give me the rate at which something is changing, the rate at which that amount is changing. So for example, if water is being drained from a swimming pool, R of T is the amount of water in cubic feet that's in the swimming pool. R prime of T would be the rate at which the amount of water is changing. And so let's think about what the units would be. When I do these units, it's the units of R, and it will be divided by the units of time. My time was measured in hours. So whenever I take the derivative, I add on a per whatever, in this case the time units, but it's really the independent variable, so that's the one you're plugging in for. So if R was in cubic feet, then R prime of T would be in cubic feet per hour. So we turn it into a rate. Now, if I integrate a rate, it's going to give me the amount of change. So that's going backwards from what we had talked about before. So if I integrate a rate, it gives me the amount of change. So for example, if I integrate R prime, which we said was the rate at which the amount of water was changing, I get R of B minus R of A. That's the amount of water at A and B. And I'm taking the difference between them. So this is the change in amount of water in cubic feet. I have to give what units those are, from t equals A to t equals B hours. Now, if you're not sure about these units, pay attention to what our function was. We calculated R of B minus R of A, and we know that R was measured in cubic feet, so my answer for this integral should be cubic feet as well. In number 4, we're looking at a time interval from 0 to 22. The rate of change of the population of deer in a forest in deer per month, I would underline that unit, it's going to be important, can be modeled by the differential function c of t. T is measured in months. It tells me that at time t equals 19, there are 200 deer in the forest. What is the best interpretation of this statement? The integral from 19 to 22 of c of t dt, which is 75. So if you think about what we just talked about, c of t was measured in deer per month. If I integrate this, this is going to give me deer. So this is saying something about 75 deer. And so that means it's actually talking about the population. So if c of t was the rate that the population changed, then the antiderivative will be the amount of population change. Since this is positive, then that means the number of deer increased. So I can say the population of deer increased by 75 deer. And then don't forget your time, from t equals 19 to t equals 22 months. In example 5, we are looking at an interval from 0 to 11. We have the amount of water in a tank in liters, can be modeled by this function w of t. At time t equals 1, there's 48 liters of water, and it's asking for the interpretation of this integral, 1 over 11 times the integral from 0 to 11, w of t dt, which is 47. So notice in this case, w is not a rate, and so I'm integrating this amount of water. But the key here is to notice that 1 over 11 in the front. When I see that I have a fraction coefficient, and I notice that the denominator 11 is the same as the width of this interval, what this is telling me is that this is the average of w, specifically average value. So whatever my function is here, which is w in this case, the amount of water in the tank, it will be the average of w. Now, if you think about the units for antiderivatives like we did in the last problem, this gets a little tricky. W is amount of water in liters. The antiderivative of that would actually be liters times hours, which doesn't make much sense to us. But then we're dividing by 11 hours, which is going to give us liters. So the units for the average value will be the same units as the units of W, whatever is your integrand is, the inside of your integral. So this will be in liters. So this is the average of W, so the average amount of water in the tank from t equals 0 to t equals 11 hours is 47 liters. In example 6, we have a very similar problem. We're looking at a function n of t, and that's the amount of water in the tank. I'm going to underline that. Pay attention always, is it an amount or a rate? And t is measured in hours. Notice our units here are gallons. We got to pay attention to that. At time t equals 5, there's 26 gallons of water in the tank. What is the best interpretation of the statement 1 over 11 times the integral from 0 to 11 n prime of t dt equals 22? And so hopefully, again, you notice there's this 1 over 11 in the front. That's telling me that this is an average. And so it is the average of whatever my integrand is. That's the average of n prime. But what you'll notice is n prime is a rate. N was an amount. I take the derivative of that. This is a rate. So that means this is the average rate of change of n of t. So the average rate that the amount of water is changing. Again, since this is positive, I know that my amount is increasing. So I could talk about that, but really what I'm just going to say is the average rate of change of water in the tank is equal to 22 gallons per hour. Remember, my units here will match the units of the integrand. N prime would be gallons per hour. And then don't forget your time interval. So from t equals 0 to t equals 11 hours. Now let's try a free response question. This is very similar to a problem you might get on the AP exam. It does tell me I can use my calculator, which is handy dandy. So we've got cows on a small dairy farm in northern Indiana. They're milked in the morning during a 2-hour period. Milk from the cows is pumped into a storage tank, and the volume of milk in the tank at time t is modeled by a strictly increasing twice differentiable function. If they're telling you your function is increasing, you might want to underline or highlight that. It's going to be important to your problem. They will not tell you that if you're not going to use it somewhere. M is measured in gallons, and t is measured in minutes. We'll keep that in mind. And at time t equals 0, there's 300 gallons of milk. We have a table of values for m of t. Part A asks us to estimate m prime of 70, and we'll use in units of measure here, and then also explain the context. So if I'm given a table of values and it's asking me to estimate a derivative, remember that's slope. So I'm estimating using slope, or also you can think of it as average rate of change. So I don't have the point 70. I'm going to use the 2 points nearby, 90 and 50. Y values on top, m of 90 minus m of 50 over 90 minus 50 equals 3,360 minus 1640 all over 40. Now you can leave your answer here if you put units. I will go ahead and simplify it. Even if it's a calculator problem, you can leave it right there with units. I'm going to simplify it because it'll make it a little easier. That is 43. Remember, you can use your calculator to simplify that. The units would be, I noticed I had m over my time. Units of m were gallons, time was minutes, so this is gallons per minute. Now let's give the context. So m is the rate of change, m prime is the rate of change of m. M was the amount of milk, and so this is the rate of change of the amount of milk. Since this is positive, I know the amount of milk would be increasing. So the amount of milk is increasing by 43 gallons per minute at t equals 70 minutes. Remember, the derivatives are at specific time periods. Integrals are over a time interval. So derivatives at a certain time, integrals are over a time period. Part B asks me to use the data in the table to evaluate the integral from 0 to 120 of m prime of t dt. Using correct units, interpret the meaning of this in the context of the problem. Now, you have to pay attention to what you're given versus what you're trying to integrate, because then you will handle these problems differently. Here, I'm integrating m prime. I do not have m prime, I have m. So I need to somehow get m prime to be m. I need to do something with it. And so what that means is I need to integrate it. The antiderivative of m prime is m. So if I just take that antiderivative, I can calculate it. So the integral from 0 to 120 of m prime of t dt would be m of 120 minus m of 0. So antiderivative is m, and then over the interval here. I have those values up in my table. 4,250 minus 300. That gives me 3,950. My units here are gallons because I'm doing m minus m, and the m was measured in gallons. Now what this means is pay attention to what I just had, m of 120 minus m of 0. That's the change in the milk from 0 to 120. Remember, integrals will give you an amount of change. So this means from t equals 0 to t equals 120. And let's put units on that. These are minutes. 3,950 gallons of milk have been added to the storage tank. Our last problem, part C, it says use a right Riemann sum with 4 subintervals indicated by the data in the table to approximate 1 over 120 times the integral from 0 to 120 of m of t dt. Explain the context, and then we'll decide if this is an overestimate or underestimate. So again, pay attention. I'm integrating m of t here, which is the function I'm given, which means I would use area. That's why we're doing Riemann sum, because the Riemann sum is area. So start out, don't forget your 1 over 120. I'm going to go ahead and rewrite that integrals just so I can keep track of what I'm doing. M of t dt is approximately equal to, remember Riemann sums are approximation. I just leave the 1 over 120 out in front. The Riemann sum is going to approximate my integral here. So let's go back up to our table of values. We're doing a right Riemann sum. So I need to find the width of the interval. This is 20. And then I'll use the height as the right value, 780. Then 30 times 1640, 40 times 3360. I'll write these out. And then 30 times 4250. Even if this is a calculator problem, you must write this setup, not necessarily on the table. I'll show you how to write it. But you must write that setup in order to get credit on the AP test. If you just do all the calculations in your calculator and put the answer, you will get 0 points. So we said it was 20 times 780 plus 30 times 1640 plus 40 times 3360 plus 30 times 4250. Now, as long as you put units on this, you could leave your answer right there on the AP test. And I would actually recommend you leave it there. Do not simplify it if you don't have to. Even if you have your calculator, you might mess something up. And then for my description, I don't even necessarily have to rewrite that. I can say just what it means. So I was taking 1 over 120 times the integral of m of t. That 1 over 120 tells me that this is an average. It's the average of m. So in this problem, that means it's the average amount of milk. The average amount of milk, or let's say this is, just to refer to it so I don't have to rewrite it, this is the average amount of milk in the storage tank from t equals 0 to t equals 120 minutes. I don't need to, as long as I put units up on this answer, I don't need to put that value back in here as long as it's written there on my page. Now the other thing it asked me is this an overestimate or an underestimate? We were using a right Riemann sum, and it did tell me my function was increasing here. A right Riemann sum would be an overestimate because I'd be using the right endpoint as the height. So I just need to say that. We could say this is an overestimate since m is increasing and a right Riemann sum was used. Just keep it really simple. You don't have to explain why an increasing function means that you're an overestimate. Just this is an overestimate since m is increasing and a right Riemann sum was used.